Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to wrap up our conversation about bonding by taking our ideas of molecular orbital bonding and bringing them up to full kind of chemical systems. So one of the first things we can do is take our techniques from diatomic homonuclear systems and expand them to heteronuclear systems. So this is simply where I've got two different atoms. So the basic idea, if I've got two different atoms, is I'm going to want to start with my atomic orbitals in the valence shell for each of these atoms. So for a carbon, I've got my 4 electrons spread out over the S and P shell. And oxygen, I've got 6 electrons. So I've got 10 electrons total that need to be mixed up. Now, the first and probably the biggest difference in between homo and heteronuclear systems is that my atomic orbitals will no longer be at the same energy level. So somebody is going to have orbitals that are more stable. And in general, it's going to be the more electronegative atom. Think about it. The more electronegative atom wants electrons more, so it probably has lower energy levels. That way, the electrons are going to want to be there more. And when we mix up our orbitals, that's exactly what we see. So for example, if I mix up my 2s orbitals from both systems, the 2s orbitals are still going to mix with each other. They're going to make a bonding and an anti-bonding electrons. And the bonding will go down about as much as the anti-bonding goes up. These 4 electrons will mix together and won't have a big major effect in this case. However, when we're mixing together the p orbitals, that's a little different. Now, in this case, what ends up happening, since the oxygen has such a low set of p orbitals and the carbon has such a high set of s orbitals, what ends up happening is we see that the sigma orbitals tend to chase each other away. And honestly, this is something that takes a lot more experience than you'll currently have to try and predict what the order of these sigma and pi electrons will be in a true heteronuclear system. Sometimes the sigma will be lower, sometimes it'll be higher. And again, I will try and provide that information for you when relevant. But in this case, the sigma is higher. And so the pi orbitals will fill up first. So what we can then do is say, I've got 10 electrons that came in with valence electrons that came in with carbon and oxygen, and we'll walk our way up. The first 4 go into the s-based orbitals, and the next 6 go into the p-based orbitals. That will mean that we'll fill up both the pi and the sigma bonding orbitals, and we won't put any electrons in the anti-bonding orbitals. As a result, we're going to end up having a bond order of 3. And that's the real good take-home point of what we can use these MO diagrams for, is we actually confirm that carbon monoxide, exactly like Lewis structure would predict, has a bond order of 3. However, this won't always happen, and sometimes you'll get some real surprising results. So in general, the biggest difference that we're going to find from homo versus heteronuclear is going to be this offset of the energy levels. And remember, more electronegative, lower in energy. However, it turns out the whole world isn't just made of dinuclear molecules. Now, while these are very cool for gas phase related species, such as carbon monoxide and nitrous oxide, a lot of times we want to deal with polyatomic systems, like in this case, our old friend ozone. Now, trying to build a full MO diagram for these polyatomic molecules actually can be really difficult, as there's going to be a lot of different orbitals that can mix together, and you're never sure which ones will mix with which ones. So in this case, what we're going to have is something we can get a little information about from our Lewis structure and Vesper. So we know that we're going to have a sigma network based on our electron domains that is going to have 1, 2, 3, 4, 5, 6, 7 sets of orbitals, giving us 14 electrons. However, oxygen, I've got 3 oxygens, each with 6 electrons apiece, meaning I've got 4 extra electrons that aren't going to be in this sigma network predicted by Vesper. So as Vesper would say, the rest is probably going to be in my pi network. Now, The question is exactly what are these sigma orbitals and pi networks going to look like? And the answer is a little bit messy. So it turns out that, again, we could get this idea from Vesper. We will indeed form two sets of bonding orbitals, one linking this set of oxygen atoms, one linking this set. They're both going to be degenerate, and in truth, they get a bit messy. The remaining set of 5 orbitals will essentially remain non-bonding. Now, a very important thing to remember is if I've got 2 bonding orbitals, I will have 2 non-bonding orbitals. However, as I fill them up with my 14 electrons, you'll note that we're only going to fill the bonding and anti-bonding, or the bonding and the non-bonding, and the anti-bonding remains unoccupied. Now, I'm not going to ask too much about sigma networks because they get really messy and they're way beyond the scope of this class. However, one of the very cool things is it turns out these pi networks will obey a lot of the same rules that we found for homo and heteronuclear systems. So we know that each one of these oxygen atoms will each contribute a single p orbital, and that I have 4 leftover electrons that aren't caught up in this sigma network. So what we can do is, using this basic idea, I know that I've got 3 orbitals that are coming in, and so if I mix 3 orbitals, I should end up producing 3 orbitals. And one of the biggest things is that the orbitals, when I mix orbitals, I'm always going to produce one combination that's as favorable as possible. And we know electrons love to spread out. So my most favorable set combination is going to produce a pi bonding orbital where the electrons can move from one end to another smoothly. And for every time I produce a favorable orbital, I'm going to produce a very unfavorable orbital where I'm going to have a node where I have to switch directions of the density every time I go from one atom to another, because this will make it very hard for the electron to move throughout the system. So this produces my anti-bonding orbital. And as a result, the last one is going to be what we call a non-bonding orbital. There's going to be one node in the middle that doesn't allow any movement from one set of electrons on one p orbital to another p orbital. So what I have when I end up putting these remaining 4 electrons in the system is I've got 2 electrons in a bonding orbital, and I've got 2 electrons in this non-bonding orbital, and then I have all my leftover parts making this unfilled, very unstable anti-bonding orbital. And again, an important thing to note is anytime we have an odd number of orbitals that are going to be present in a mixing, and this doesn't really depend on the circumstance, you're always going to produce a non-bonding orbital, because think about it. If I mix 2 orbitals, one goes down, one goes up. If I've got 3 orbitals, one goes down, one goes up, and one can't go anywhere because nobody will mix with it. And that's kind of what we have in this case. Now, one of the very cool things we can do with this sort of simple MO diagram is compare it to our Lewis structure. And if you remember, our Lewis structure for ozone produced a resonance structure, one where I have a pi bond in between one set of oxygen atoms and one where I have a pi bond in between the other set of oxygen atoms. Now, when I compare this to the MO diagram, what I find is I've got a pi bond in between all 3 oxygen atoms. So a good way to think about it is that, to a certain extent, what I'm seeing is that this pi bond is going to be 50% of the time between these two, 50% of the time between these two, but 100% of the time between this one and somebody. And that's exactly what we see in the resonance structure. So resonance actually has its root in MO theory. Now, the really cool part, though, is when we're talking about those non-bonding orbitals, because what we find here is that 50% of my non-bonding character is on this terminal atom, and 50% is on this terminal atom. And this means that, indeed, the resonance structure is also correct. 50% of the time, this oxygen atom is going to have 3 lone pairs, and 50% this oxygen atom is going to have lone pairs. The biggest difference when we're looking at MO theory is that it's showing that this is all happening simultaneously, because the electrons aren't on one or the other. They're on both, just not evenly. not all the time. And this is a very kind of cool and nuanced piece of information we get out of MO theory. And so this is really what resonance is telling us. And one of the things we should keep an eye out for on resonance is that it represents the fact that electrons tend to not be localized on any given atom. They spread out. And so trying to put them discretely between two atoms or on one atom often misses the point of what electrons really want to do. Now, one of the other very cool things we can do with this MO theory is we can expand it to much longer pi systems. So you can see this a lot of the time with pi networks. So what we can do is take a whole bunch of carbon atoms, all with sp2 characters. So each one is bringing in a single pi orbital, and we can keep extending these pi networks. So if I have one carbon atom with a single p orbital, I have a single p orbital. If I have two carbon atoms, well, then I get something like ethene, and I have a bonding orbital and an anti-bonding orbital, with the two electrons wanting to occupy the bonding orbital. However, as I add in more and more orbitals, what ends up happening is I keep adding more bonding orbitals. However, what happens is that, kind of as we saw with ozone, if I have an odd number, I have one orbital that will go down, one that stays the same, and one that goes up. If I add in four orbitals, one goes down a lot, one goes down a little, one goes up a little, one goes up a lot. And so as I add in more and more orbitals, you can think about we're adding them in this kind of non-bonding character and pushing our favorable orbitals more favorable and our unfavorable more unfavorable. And this generates something we call a HOMO-LUMO gap. So this is the difference in between our highest occupied orbital, so HOMO, and our LUMO, the lowest unoccupied molecular orbital. And this actually has some real important applications to chemistry, because as we've seen previously, we can actually make electrons move from one orbital to another using light. And as we make these two orbitals become closer and closer in energy, as these carbon chains get longer, well, eventually we get to the point where I can excite an electron from the HOMO to the LUMO using light. And this is actually how we get colored organic dyes. So if anybody talks about organic dyes, what they're talking about is long carbon chains where they've gotten long enough that these orbitals start converging on each other to the point where the difference in energy is going to be achievable by adding in a photon with visible spectrum light. And so this is one of the reasons why we tend to care a lot about pi networks. And they can also accomplish a great deal of very cool chemistry. Also, one of the other very cool things about pi networks is they're often very good at stabilizing molecular species, especially if you can take these pi networks and, instead of making them a long chain, wrap them around in a circle. So if you have a carbon system with 2n+2 carbon atoms, one of the things you can do is make a pi network that you can make into a cyclic compound. The most common of this is going to be a 6-membered ring, which is called benzene. And one of the reasons why these species are very cool is because you can start producing degenerate energy levels. And like we've seen before, if I've got 6 carbon atoms, this means I'm going to have 6 orbitals. So 3 of them will go down, 3 of them will go up. The most stable of these bonding orbitals means that I'll have no nodes along the whole circle. So the electron can quickly run in circles around the entire benzene molecule. However, you're going to have a slightly higher energy one where there's a node in the middle. So I can run around half of it at the time before I have to get up some energy and then jump over to the other side. And so that's not too bad. Now, in a straight carbon chain, the next one would be having 2 nodes. However, when you introduce the cyclic compound, what you end up is producing a degenerate energy level where you have one node that is in one direction and another node that is in the opposite direction or perpendicular direction. So each of these 2 orbitals have one node, but that means they've got the same energy level. because as we started off our discussion with orbitals about, nodes will predict the energy. And we see this again popping up even here at the end with benzene. As we go to 2 nodes, then we start seeing these anti-bonding because I've got more nodes than I have straight line connections. So it's less favorable than just these p orbitals hanging out on their own. And then of course we have the very unfavorable all nodes. But with benzene, I've got 6 orbitals and 6 electrons, which means I only have to occupy those bonding orbitals. So in the end, the system is very favorable. And you're going to see a lot of this if you go on to do organic chemistry, because the power of these resonance structures and these distributed electrons is really going to power the stability of some of the most popular compounds in chemistry. However, next time, we're going to go ahead and change to a completely different topic as we get back to chemical reactions and looking at solutions. Until then, take care.